Time is a fundamental aspect of our existence. We experience it as a continuous flow, always moving forward. But have you ever stopped to ponder why time seems to have a preferred direction? Why can't we simply turn back the clock? This is a question that has puzzled philosophers and scientists for centuries. It's a profound mystery that lies at the heart of our understanding of the universe. We can easily imagine traveling through space in any direction, but time seems to confine us to a one-way journey. The nature of time is deeply intertwined with the laws of physics. To unravel its secrets, we must delve into the realm of thermodynamics, the study of energy and its transformations. It is here that we encounter the second law of thermodynamics, a principle with profound implications for the arrow of time. As we embark on this exploration, prepare to challenge your preconceived notions and embrace the wonders of the cosmos. Our journey through time's mysteries is about to begin. The second law of thermodynamics is a fundamental principle that plays a crucial role in our understanding of the universe. It governs the behavior of energy in the universe, dictating how energy is transferred and transformed. This law states that the total entropy of a closed system can only increase over time, never decrease. But what exactly is entropy, and what does it have to do with the passage of time? Entropy is essentially a measure of disorder or randomness within a system. A system with high entropy is more disordered and chaotic compared to a system with low entropy, which is more ordered. To visualize this, think of a perfectly ordered deck of cards, where each card is in its proper place. As you shuffle the deck, the cards become more mixed up and disordered, leading to an increase in entropy. The second law tells us that the universe has a natural tendency towards increasing disorder and chaos. This means that over time things naturally become more random and chaotic, moving towards higher entropy. We observe this phenomenon everywhere around us, from the gradual decay and deterioration of buildings to the irreversible process of aging in living organisms, which is a clear example of increasing entropy. But how does this concept of entropy relate to the direction in which we perceive time to flow? Imagine watching a movie of an egg breaking. The sequence of events is unmistakable. You can easily tell whether the movie is playing forward or backward based on the behavior of the egg. In the forward direction, the egg breaks and becomes more disordered, which aligns perfectly with the second law. In the reverse direction, the broken egg spontaneously reassembles itself, an event that would violate the second law. The second law of thermodynamics provides a powerful explanation for why we experience time as moving forward and not backward. It is the direction in which entropy increases, the direction of increasing disorder, that defines the arrow of time. To understand the origin of time's arrow, we must journey back to the very beginning of the universe, the Big Bang. This monumental event marks the birth of everything we know, setting the stage for the unfolding of time itself. Approximately 13.8 billion years ago, the universe emerged from an incredibly hot, dense state. This initial singularity contained all the energy and matter that would eventually form stars, galaxies, and everything in between. In those first moments, the universe was in a state of extremely low entropy. This means it was highly ordered, with energy and matter distributed uniformly across the cosmos. It was incredibly uniform and ordered. The smoothness of the early universe is a stark contrast to the complex structures we see today. But as the universe expanded and cooled, entropy began to increase. This increase in disorder is a fundamental aspect of the universe's evolution. Matter clumped together to form stars and galaxies, and the universe became more complex and diverse. These structures are the building blocks of the cosmos, each contributing to the grand tapestry of the universe. The Big Bang essentially set the initial conditions for the arrow of time. It established a universe where time could flow in a single, consistent direction. It created a universe with low entropy, allowing for the increase in disorder that we observe today. This gradual increase in entropy is what drives the forward progression of time. The expansion and cooling of the universe provided the stage for entropy to take hold and drive the forward march of time. This relentless increase in disorder is a key feature of our universe. The Big Bang's legacy is not just the creation of matter and energy, but also the establishment of time's directionality. It set the parameters for how time would unfold, giving us a universe with a clear past, present, and future. It is a testament to the profound interconnectedness of the cosmos, where the very fabric of space-time is intertwined with the fundamental laws of physics. This interconnectedness ensures that the arrow of time is a universal feature affecting every part of the cosmos. We often think of time as a linear progression from cause to effect. An action occurs and its consequences unfold in the future. This cause and effect relationship is so ingrained in our perception of reality that it seems almost self-evident. The arrow of time, dictated by the second law of thermodynamics, underpins this cause and effect order. As entropy increases, it creates a clear distinction between the past and the future. The past is fixed and immutable, while the future is open to possibilities. Consider the simple act of dropping a glass of water. The cause is the release of the glass, and the effect is the shattering of the glass upon impact. We instinctively understand that the shattering cannot precede the release. This temporal order is a direct consequence of the arrow of time. The arrow of time, therefore, provides a framework for understanding causality and the flow of events in the universe. It is a fundamental principle that shapes our perception of reality and governs the unfolding of events on both cosmic and everyday scales. Section 5. Time's Shifting Symmetry, a Tale of Two Scales. While time seems to flow inexorably forward on the macroscopic scale of our everyday experience, marking the passage of days, months, and years, things get a bit more complicated when we zoom into the microscopic world of atoms and subatomic particles, where the rules of time are not so straightforward. At the microscopic level, the laws of physics exhibit a remarkable symmetry with respect to time, allowing particles to move in either direction. This means that the equations describing the behavior of particles are equally valid whether time is running forward or backward, a concept that challenges our everyday understanding of time. In essence, there is no preferred direction of time at this fundamental level, making the microscopic world a realm of time symmetry. However, this time reversal symmetry breaks down as we move to larger scales, where the direction of time becomes more apparent. The second law of thermodynamics emerges from the statistical behavior of vast numbers of particles, dictating that entropy, or disorder, always increases over time. This creates the arrow of time that governs our macroscopic world, giving us a clear sense of past, present, and future. The apparent contradiction between time symmetry at the microscopic level and its asymmetry at the macroscopic level is a fascinating puzzle that continues to intrigue scientists. It suggests that the arrow of time may not be a fundamental property of the universe, but rather an emergent phenomenon arising from the complex interactions of countless particles, revealing the intricate dance between order and chaos. Section 6. Quantum Quandaries, Time's Two-Way Street. Quantum mechanics, the theory governing the behavior of matter at the atomic and subatomic levels, introduces even more intrigue into the nature of time. In the quantum realm, events are governed by probabilities rather than certainties, and the very act of observation can influence the outcome of an experiment. Some interpretations of quantum mechanics suggest that time might not be as straightforward as we perceive it. For instance, the many worlds interpretation proposes that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. In this view, all possible timelines exist simultaneously, and our experience of a single, linear timeline is merely an illusion. While these ideas remain highly speculative, they highlight the profound mysteries surrounding the nature of time in the quantum realm. It is possible that our classical understanding of time as a linear progression may need to be revised as we delve deeper into the quantum world. Section 7. The Universe's Destiny. A glimpse into time's crystal ball. The arrow of time has profound implications not only for the past and present but also for the ultimate fate of the universe. As entropy continues to increase, the universe will eventually reach a state of maximum disorder, known as heat death. In this scenario, all stars will have burned out, and the universe will be a vast, cold, and empty expanse. No further work will be possible, and time itself may lose its meaning. However, other cosmological models propose alternative destinies for the universe. Some suggest that the expansion of the universe may eventually reverse, leading to a big crunch, where the universe collapses back in on itself. Others propose a cyclical model with an infinite series of big bangs and big crunches. The ultimate fate of the universe remains one of the biggest unanswered questions in cosmology. The answer will depend on the precise values of cosmological parameters, such as the amount of dark energy in the universe, which are still being measured with increasing precision. Section 8. Time's unanswered riddle. The quest continues. The question of why time only moves forward is a profound one that has captivated thinkers for centuries. While we have made significant progress in understanding the arrow of time, it remains one of the most fundamental mysteries of the universe. The second law of thermodynamics provides a compelling explanation for the direction of time on the macroscopic scale, but questions remain about the nature of time in the quantum realm and the ultimate fate of the universe. As we continue to explore the cosmos and delve deeper into the fundamental laws of physics, we may one day unravel the secrets of time's arrow. Until then, it remains one of the most profound and enduring enigmas of our existence.